Okay. So in the previous lecture, you guys learned about Boyle's law, Charles' law, and Gay-Lussac's law. So the only thing I want to mention before we move on to the combined gas law is Avogadro's law, which says that volume is specifically proportional to the number of moles. So N is the number of moles. For those of you keeping track, I'll write that down up here. Okay, so that's one thing that we haven't talked about yet, but it's important for the combined gas law, which I'm going to write down right now. Okay, so quick question for those watching. What's P stand for?
Pruitt.
It's Pruitt.
Pressure.
Pressure. Okay, good. Pressure. What does V stand for?
Volume.
What?
Volume.
Volume. Okay. Like the volume of my voice, or
The volume is in how much of it?
how much of something, the space it takes up? Okay. T?
Time. Temperature.
Oh.
Temperature.
I'll ask that again. What does T stand for?
Temperature.
Okay. And then N I said was number of moles, right? So looking at the combined gas law, we're taking these four laws and combining them. And so P is on top for both of these, right? For Boyle's and Gay-Lussac's, you guys follow me? So P is on top here. V is on top as well in all of the equations. So V is up here. Temperature is always on the bottom, so it goes here. Same with N. So that's why we put it together like this. So what we're looking at, I'm going to write this down. So what's important to note about the combined gas law is that we're looking at an initial pressure, volume, temperature, number of moles, and final pressure, volume, temperature, number of moles. Okay, so if you're given a whole bunch of information, it's probably going to be how something started and then how something ended. Okay, the big thing to note is that you can find any of these other gas laws, any of these four gas laws, from this one equation. Okay, pretty sweet. You guys are also going to need this equation for your 7-1 lab question, which I'm going to do next. Okay, so here I want to walk through for you guys. This is a pre-lab question, number 7B. We're looking at the volume of nitrogen gas collected in an experiment. It's collected over water at 24 degrees Celsius at a pressure of 99.1 kilopascals. Okay, this is our initial temperature that we're going to look at. And then what we're trying to find is what the volume would be at standard temperature and pressure, which is STP, right?
Yeah.
Okay. So given that, let's see. We've got to plug in some numbers. So we've got initial stuff. So one of you want to come up here and plug in the first half of this equation? Oh, he said. No, come on, Liz.
Okay.
You even get to pick your color. Yes. Look, we've got pressure, volume, temperature, pressure, temperature, volume. So you plug in the first half. Liz, what are you doing? Fruit, are we supposed to use Celsius?
No.
What are we supposed to use, Liz?
Kelvin.
You better fix that.
Yes, ma'am. I throw something at fruit now.
No. Do you need a calculator?
I do.
24 plus 273, 297.
This is all easier with a cat.
Okay, you can store
Or
information in that.
scroll.
Okay, good. That's one half. I'll do the other half.
Should I be doing this?
Yes. Okay, so Fruit, we've got pressure times volume over temperature.
Yes.
What's the question asking us? What are we trying to find?
Or the volume of N2.
Okay, volume of nitrogen gas. So we're looking for volume 2. We have pressure 2, right? Standard temperature and pressure. What was standard pressure?
Standard pressure was 101.3 kilopascals.
And what's standard temperature?
273 Kelvin.
What? Kelvin, did you say?
96.1 times.
Let's take a look at a second example problem that is similar to the one you had to do in your lab. You're given a 2.3 liter balloon that's at 15 degrees Celsius and at 570 millimeters of mercury. That's its pressure. So that's our initial set of data, and what we find is that we're going to change the balloon by taking it to negative 15 degrees Celsius and a lower pressure of 425 millimeters of mercury. Something really quick to note about this problem is that if it's not included in the problem, if you don't have a starting number of moles or an ending number of moles, then you can just leave it out of the whole equation. You don't have to worry about it. This is a very nice equation in that regard. From here, we're just going to simply plug and chug, take the numbers that we have and plug them into the equation. Let's start with pressure and volume. So we're going to multiply pressure times volume. That's what the little asterisk is. I'm including units because it can get a little hairy and a little confusing if you don't include units on the equation that you're working with. So that's equivalent to, that's equal to, we're just going to rearrange this equation to solve for whatever variable you're missing. There's not ever going to be a time when you have two unknown variables. You're going to get all the information you need in one way or another. The way I'm going to go about solving this problem is a little bit different than the example problem I did from your lab. I think the way I'd like to approach this is to solve the left side, so 570 times 2.3 divided by 288, which is around 4.55, and then rearrange the equation to solve for V2, or the second volume. So to divide by 425 and multiply that whole number by 258. So just doing the numbers out, we end up coming out with about 276 for a new volume. So that's going to be 2.76 liters.